So yesterday we covered. Good morning, everybody. About architecture of Yokogawa Centum VP DCS installed in the plant. Now we will discuss about how it is installed actually in the plant. What are the components required? So just see here. Uh, First, field devices, then junction box, then marshalling cabinet, elco board, then node unit. You can see the how the signal is input output signals are processed. Elco board, then ESB. You can see first node unit. Then this input outputs are processed and it is taken to through ESB bus. ESB is a dual redundant. Then another NUU. So you can have 9 NUs in this plant. So it is shown like a 9, 1 to 9. And then finally, the signal is coming to the CPUs, and CPUs are redundant. So you see the CPU. Yesterday we have seen FCU, rack, and then VNet IP control network, which is again dual redundant, and these are HI stations 1 and 2. So this is what yesterday we have seen in the Centum IP architecture. So you have to remember this. This is very very important for you. HIS, VNet, FCU, node unit, Elco board, marshalling cabinet, junction box, then field devices. So this is what yesterday we have discussed. This I'm skipping fast because we have already shown you all this yesterday. Single CPU, duplex. This is what was shown yesterday. We have covered it, rack and all. And now actually plant installation we are going to discuss. Uh, so you can see here this closed loop implementation in Yokogawa DCS, level transmitter, JB, marshalling cabinet, elco board, and this is the AI card. Actually, AAB841 is the product identification number of that Yokogawa company. So, but as in general, we call as AI, then ESB bus and controller. So finally, signal is coming to the controller. It is a PID block, is a software block is processed here, and then output again goes back to this loop 4 to 20 milliampere I2P, and 3 to this 3 to 15 psi goes to the LCV 101, and then the status of this loop is displayed on the HIS. So as I told yesterday, also some of these nomenclatures, but only analog closed loop card number is AABV841 is this product name specific. So now we will discuss how a system is implemented in the boiler plant. So in short, you can see here what is a boiler. As far as our boilers are, RCF boilers are concerned, plant capacity is a 510 tons per hour with the 3 boilers. So SGP means steam generation plant consists of 3 boilers, each capable of generating 170 tons. So that becomes 510. Uh, and steam at 105 ATA. ATA is the pressure unit, and temperature is 510 degrees centigrade. So boiler type is a boiler make is from Bhel, manufacturer is a Bhel, Bharat Heavy Electrical, Hyderabad. Steam supplied, whatever steam is manufactured here, produced here, is going to the ammonia plant and further downstream other plants through associated gas compressors, because you require different pressures. So through compressor it is distributed to the other downstream plants like nitric acid, methanol, and else others. So if you see the boiler, there are three critical loops: drum level control, combustion control, and feed water flow control. Uh, As per the specification, we discussed the temperature, pressure, and capacity. Uh, Something brief about a boiler. Actually, our today's session is not related to the boiler, but just you can read it. Hot gases are directed to around means this is what our is a water tube boilers, usually rectangular in shape and have two or more drums. We have two drums. The separation of steam and water takes place in the top drum, while the bottom drum serves as a collection point for a sludge. So straight away come to the Yokogawa DCS hardware. Input output cards. This is the size of the system. Input output cards in the boiler plant is closed loops are all redundant, and these are 4 to 20 milliampere analog inputs and 4 to 20 milliampere analog output. This is our requirement for the boiler. And as I told, the analog input the card used here AB841, and it has see here number of IO modules means such type of a 10 cards are used. For open loops, 4 to 20 milliamp analog input, the card name is this, and 6 cards. RTD inputs, the name of the card is this, AAR145, one card. Thermocouple input, AAT 145, only one card. Then digital, I mean, discrete signals, digital inputs redundant, ADV 159, 26 cards. See how much interlocks are used in the boiler. Because each card is a 32 channel and such type of a 26 cards. Digital output redundant ADV 559, 12 cards is 6 into 2 redundant. Digital output ADV 2 cards. So total 58 cards means in the rack. If you see IO racks and all, there will be 58 cards will be there, which are required for controlling of the boiler plant. Now I'm coming to the one loop, boiler feed water level control loop. As this is also one of the, as I told, combustion control, drum level control, and boiler feed water level control is the critical loops. And out of that one level control loop, we have selected for demonstration purpose. So the tag here is a 2LIC1034. This is a tag name, 2LIC level indicating control 1034. So you can see here, uh, field area, control room area, process area, junction box area, analog marshalling cabinet, and system cabinet. These are this way it is divided the box location wise. So in the process area, you have a field transmitter installed here, and that is shown with a symbol with two wires plus minus, and you see here a cable number, pair, field tag. Entire thing is tagged on this wire. When you see the any field cable, you'll find a tag, and there you'll find cable number, pair, core number, and field tag means LT whatever 103 or 1034, like that. This will be there. And this wire cable is terminated at a junction box here, and again junction box has a cable number, pair number, JB number. Here you can have a JB number, and there in the JB, which terminal it is connected, everything is you can identify through these tags. Then from this JB, entire multi-pair cable. This is a multi-pair cable. This is a single cable, because in this JB, the whatever devices are there in this loop nearby, they are terminated through the JB, and this JB carries entire signal on multi-pair cable, and this multi-pair cable coming to the analog marshalling cabinet here. You can see this cable has terminated here, and you see here terminal termination at what point. Then then this wireway goes to where, whether it is routed through intrinsic say barrier or not. So all this you can see here elco board. This is a elco board here, and if repetition is required, then repeater takes the signal to another area like this. So you can see here, this is a redundant system. So in this elco board, you can see one cable goes to this card, one goes to another card. So you can identify here your card is here, but entire thing is mentioned, which FCS, which NEU, which slot, and which channel. Entire thing is mentioned on your tag. Similarly, for redundant also same thing. Which FCS, for example, here FCS is F1, NEU 1, slot 2, and channel 2. Like this, it is a mention, so you can identify where it is connected. Actually, as far as the maintenance is concerned, we do maintenance up to the marshalling. Beyond this part, we don't have to do anything because all prefabricated cables. So beyond marshalling cabinet towards the system, we normally don't need to do check the wiring. Our main role in the field side, transmitter, junction box, and this termination in the marshalling cabinet. Same thing for this. So now I'm just briefing about the boiler feed water. So boiler feed water is very deaerated water is required. First of all, very pure water, because a boiler efficiency, if you have to maintain, then silicas, other foreign material has to be removed. So that is called a deaerated. For that purpose, always we are taking a water from municipal corporation, and that water we have a water treatment plant. Treatment plant, there we treat this water, pH and all, as I told, conductivity, everything is monitored. And this water, eh, that is a deaerated water, is pumped in the boiler feed water pump at a pressure of 145 kg. Means your pump is with this pressure, putting on your this boiler feed tank, this water. So capacity of boiler feed water tank is 85 tons, and the level of the feed water tank has to be maintained at a 40%. This is what requirement, operating specifications. The level of the, as I told, the capacity of the tank is 85 tons. Pressure with the 145 pressure, that pump is putting the water inside the tank. Then level always you have to maintain 40%. Below that, if it goes, the plant will trip. The level, so level control loop for this water tank is having a tag of 2LIC1034. So this level control is very very important, as far as because if the water is not maintained, then how means entire further power processing part get affected. So now first of all, I will show you the picture of actual feed water tank. So this is the feed water tank. You see, as I have to 85 tons, and what pressure, temperature always is there, substantial. So it is insulated. So you see, this is the tank where water is deaerated water is coming, and this water goes to the boiler, right? So I have shown the actual picture installed in the boiler. Is a This is a what feed water tank, and on this feed tank, level has to be maintained is a 40% minimum. So for that purpose, we have a LT1034 is a transmitter which takes care of the level measurement here. Okay, so if you see here for the picture, level transmitter, which is measuring the level of the tank, is installed on this tank, which is here. You see the differential pressure, means at top level and bottom level, tapping is there, and you see here this is a differential pressure for level measurement. So as this transmitter is a polythene covered, slightly you cannot see, but it is, the transmitter is here, right? Mm, I'm talking about LT, because we are talking about two LIC 1034 is a level control loop of this. So this is a transmitter. Now from the transmitter, the signal is a photocontroller goes to the JB. So you can see the junction box nearby here is the JB. This is the JB. Actually, you see this how terminated wires are coming here, and from here wire goes to the marshalling cabinet. When this junction box cable to control room goes from the door from here. These are from coming from the fields, and these are the incoming pair of the cable, and these are outgoing pair of cable, right? Incoming, outgoing, and you see the termination here. When you open this, you can see how the terminal strips is there, internal wiring JBs are there, and you can see here these wires are bundled together now. That indicates that it is on single pair, it goes to the marshalling cabinet. So you can your the slide is for GB, right? The actually control room, from the JB signal goes to the control room where it goes to the marshalling panel, then Elco board, NU, FCU, and HIS like this. So I'm taking you to the control room. So you see the control room here. This is our control cabinets where your this side will be marshalling, then Elcos, and then last you can see the FCU cabinet where NUs are there. Means you can see here also color of the cabinet. So these two cabinets are very important where you can have FCU and NUs, IO cards. So remaining you can see here marshallings and LCOs. And these are HIS stations, four numbers of HIS. This is what security keyboards and through this operating staff is operating here, right? So this is the what control room look. So I will show you marshalling cabinet now. So this is the marshalling cabinet where you can see the field signals are coming, wires are terminated again here and goes to the elcos, elco board for duplication isolations, right? You see the in these wires numbers are there, ferrules are there. You can see here the ferrule, each ferrule is showing from where this cable has come, and it is documented also. And in between there is a fuse link. You can see this is a fuse in between here. Any short circuit, it is protected here also. You can see this is open one, this one. So this is the fuse here inside, and when you push it to get it connected like this. Now I'm showing you elco board. So these are the elco boards you see here. This one. Two means prime, one redundancy. If it is required, it is there. You see the elco boards. So you can see from Elco board later on the signals are prefabricated cables like this. You see, so no access after that to the user maintenance point of view. Up till beyond this, during the commissioning, it was once it is done, no need to maintain also. I think so. This way, the Elco board is there, and as I told you in the Elco, for example, this is actually you can see here, two wires are going out from here means these are redundant wires. So signal duplication. This is signal way duplicated like this. So this is the Elco board electronics. Actually, Elco is the name of this electronics conversion unit by Yokogawa. Nothing else. So now I'm showing you NU. NU means node unit. So this is your one of the node unit. You see here FCU, and another below is node unit 1. So two power supplies, two controllers, ESB and IOs. Again here two power supplies, ESB communication module and IOs. Like this, use the cards are here. So from Elco, you have seen the tag, the cables are coming directly to the terminate to the cards, individual cards. So node unit actually looks like this. This is a system cabinet where on the top is FCU and below that three racks are NU 1, 2, 3, and you can see it is nested through ESB connection. You see, and then termination. If you can extend also further, but suppose on this FCU only three this much is there, then your termination is there here. It is a terminated. This cable ESB cables are terminated. As you can see, there is a no looping means it is a terminated. So actual detail diagram you can see here. Power supplies, ESB modules, how it is nested, is coming from top, then going like this, like this. ESB bus connectors. These are two spare IO modules. These are spares, and remaining this it is 8 IO modules. And then FCU unit, main unit, CPU unit. So main rack is FCU, where two power supply redundant, controller redundant, ESB and IOs. And then VNet as I told, primary switch, secondary switch. Actually, this one is a primary, yellow is a primary, and blue is a secondary here. Hmm. And then it is connected to VNet. VNet is connected through VNet. It is connected to the HIS. This is HIS. This is a workstation, human interface station. So this is about the system. Status on HIS. When you see actually through software on HIS, you can see the actual hardware here. You can see FCU, FCS1, FCS2, FCS3, FCS 103, 104, FCS 105, and FCS 106. So that much FCS are shown here. And HIS you can see 1, 2, 3, 4, 5, 6, 7, and this is not connected, so it has not. So total 3, 6, 7 HIS. Total 8 are there. Out of this, one is not working. So when you see on HIS system capacity, you will get this uh, picture. Actually, what is wired, what is in use at your plant. So system status indicator of HIS. System status. See, there are indicators are there. You can see here this indicator. Not ready, standby, in control, control hard ready, and on maintenance mode. So these are the colors showing. For example, when it is a green, most of this green means it is in control, and this means this color shows on maintenance. Certain loops are on maintenance. So you can see here actual rack here, power supply controller or cards you can see here, status of the cards. I'm talking. I have shown on the screen of this, but this is possible only on an engineering station where engineering software is there. You can see actual hardware, actual configuration there. Remaining is operation requirement. So operating staff use for their process operation requirement screens and tags and faceplates. So you can see HIS graphical view of process. This is how the process is with the multiple windows we call it. You can say background. This is the tank. What to actually I have shown you the same is graphically shown the actual level of this and control loops, input and output PNIDs, process flow diagrams. You can see here, and then critical trends, faceplates, alarms. You can see this is what you have multiple options at a one screen. So actually this is one of the boiler control room. As I told you, HIS, marshalling cabinet, elco boards, IOs, and this is a system cabinet. This is a printer. This is auxiliary console for boiler it requires, and these are electrical panels for electrical controls. So input side I have shown, and output side, the wall which is controlling the water flow is this one. You can see here this wall. This is the wall, and you can see this is the wall, and these two for isolation purpose, for maintenance purpose, because it's a high pressure, temperature is high, so is insulated. When you have to maintain, then you can have a bypass line, and through this it is isolated, and you are taking for maintenance. So this is the main control wall in the loop. I have shown the transmitter, and I2P will be somewhere here. You can see the I2P. So wall install for this is here. So this is after I'm talking about this wall. Actually, I'm coming back here. The tag I'm showing. I'm talking about this wall LCV 1034. That is what it is shown in the actually photographs is indicating that much. This one LCV. Even it is written, but slightly because in the field you are not able to read it. Mm. So this is about uh, overall this DCS in Yokogawa. Further part, it is that how it is mm, I mean software wise, how it is configured, what are the steps. So that we'll see now. So I will switching to the another presentation where how graphically it is uh, represented. Mm. So you can see here. mm, uh, I have shown this earlier. I am just coming to the our DCS part. Mm. Here I am showing. Mm. So ammonia plant, we have a condensate level control loop, 03 LIC 103, and but this condensate level control is very critical in the ammonia plant. There two systems are there. One through DCS control, and another is a emergency shutdown system control. So you can see here condensate stripper equipment here, process equipment, and there are two transmitters for level control for this. One is LT103 and another is LI104. So both transmitters monitoring the level. One is a controlling, but you can see here uh, this loop is going to the DCS, and this loop is going through uh, some uh, critical system, emergency shutdown system, very special category of the system it is going. So we'll discuss it that latter stage, but we will take it this input to the DCS of the Yokogawa. So you can see JB to Elco board, node unit, then process RS field control station and HIS VNet like this. However, as this loop is controlled through auxiliary console, means normal earlier control like push buttons, indicators. Through that you can control. I will show you the auxiliary consoles pictures, and at the same time the level control wall here control wall is operated through two outputs, DCS as well as emergency shutdown systems output. So you can see here the wall positioner and the this suppose if this DCS output fails to control, then your emergency shutdown system will on or off. There are two solenoids which are redundant also. Here solenoid is also redundant, and wall will be uh, safely safe position, we can say fail safe position, whether it is a open condition or on condition, that way it is operated. Even this also fails, this fails, this operating staff operate from here and control the wall. So that way criticality is there in the this area. When the system like DCS is 99%, we say reliable, but still we operate through emergency shutdown system. Is- Then also third, we have a human interface station like auxiliary console is there. So I will show you the auxiliary console picture first and then come back here. You see here, these are the operating staff here, and auxiliary console means this console. You see this back through these operators. Moment they have some difficulty to operate the wall from this side automatically or manually, then they operate through these consoles. Here you can see the push buttons and all these. They operate uh, through this. So this is what the control is. Now I'm coming back here. So I will show you this section is here, condenser stripper section, condenser stripper level loop for this. This is a picture, and the JBs transmitters are installed on this. You can see DCS transmitter is this one. 53 is showing level. However, this is for ESD, emergency shutdown system transmitter is there. Then DCS loop, how it is processed towards the DCS side. This is the DCS loop level transmitter as you have seen here. Rosemount make ESD ammonia stripper condenser section, DCS loop transmitter, and ESD loop transmitter. So two transmitters are there for this loop. Two JBs are there. One is for ESD, another is for DCS. So Yokogawa DCS controller, there are three FCS. This is the old system, and the system earlier you have seen was the latest. So that is the Centum VP, and this is the Centum CS controller. So that was the change here. You can see here. You can see here. This is FCS rack power supply earlier systems. This is as I told, when system is migrated towards the newer version, you will get a very size wise, speed wise, use wise, everything you will get a benefit. You see the that time in Centum VP cables, network cables of these types. Network switches are then there. Then you can see this is a new system, power supplies and a V8 V converter for redundant switches. So ESD system is the ProSep is the name of product. I'm skipping that part now because we are. I have to show you how the system is configured now, because I have already discussed about the hardware of the Yokogawa, and time is very short. We'll have some other day emergency shutdown system. So I will explain you that system. But you see the how the graphic representation screens are there. Process condenser stripper with the face plates. You see this is actual face plate, this is the process area, and you see entire this level on the face plate, also level for the operating staff actually in the graphical in the tank picture real time these values are coming here, right? Like this way the you can see uh, graphics with the face plates. This is a face plate, and this screen shows the actual loop configuration, which is not required for operating staff, but this is for instrumentation engineer. So simple closed loop is indicated here. You see this is one closed loop, this is another closed loop, like this is a third closed loop like this. So in, out, this is the field tag, this is one another closed loop FIC10, in, out. You see here, this is the input side, this is output side, and this is your PID block, PID block, PID block, PID block, PID block, PID block, like this. Splitting actions here in the PIC, the action splits. So this way you can see the actual working maintenance with the help of a color. This is working, I think. As I shown the colors now, so through that you identify this. So condenser triple level loop configuration, you can see here, broader picture. There is a in a Yokogawa, you see the percent Z IO 3 LIC 10. This way they have system to tag it percentage like this. You see percentage Z, then 003 LIC, this output side, and this is input 3 LIC 103, and this is output PID, like. And you can see the values are here, actually mentioning the values here also. That is for above picture, but you say how uh, particular loop tag LIC 103, for example, in the configuration state. This way it is done, means input, output block, PID block, and wiring like this. Automatically it becomes, and it's easy. You need not to draw it like normal PCB. Not to take a rectangle. Not it is auto. Just you click on their screen, you'll get this block. Just you give the tag name. That's all. Then suppose here also take this block and just click on here and then drag it up to here. Automatically it come here. Same thing. Drag your, this is a starting point, this is a termination point. So click on here and drag it here. That's automatic comes. So logic diagram of this I'm skipping ESD. So this is the big screen, ESD screen. You see here. This is what I was taking you to. The auxiliary console is this one, which still we maintain in the critical plant. Even our both, there are two systems: emergency shutdown system, then DCS, we say is more and more reliable, but still we have these auxiliary consoles in the plant. And these operators, senior operators, always operate, they watch it in case they require. This DCS is not maintaining the wall. They, through this, there are push buttons for that loops, and through that they control it. So I'm skipping these stripping sections and all. These pictures are related to walls. This is the wall actually used for controlling LIC. This is the wall. So digital input, digital output. So I'm coming to the actually control drawing builder here. There are two softwares: graphics and control drawing builder. As I have shown the how PID, analog input block, analog output block is there. That is through softwares. So for that purpose, control drawing builder is used to configure the basic control function of the FCS. So that is the name. Control drawing builder is a software tool for configuration. With the control drawing builder operation, such as registering function blocks uh, in the drawing file and determining the flow of means, wiring is performed graphically. So Centum AP system contains 200 control drawings per FCS. That is the capacity of one FCS. So control drawings, Centum AP system contains 200 control drawings per FCS. To access control drawings, select function block folder under FCS folder. 200 control drawings files are displayed on the right. Double click on to open the desired drawing file. So I will show the picture. So you see actually system view, and if you are in a FCS here, FCS 101 configuration, sequential library, IOM, switch, animation, here function block. So moment you click on function blocks, you will get a 200 here. And desired, if you have here, you want to this drawing, click on this like this. That is the what it was in the text format I read. So the control drawing, the picture shows the feature of control drawing environment. So how it, so this is the function block, terminate name in. Then you can see this is the wiring. This part is called wiring, and like this you see. Uh, This is as I told, percentage of pi value come to the pic controller terminated. This is a pid loop, and this is goes to output here. So this way the picture gives a total view of that environment. So if when you are working on this system, you will get a toolbar definitions. So icon button displayed in the upper area of the windows provide the same function as the menu. So both either in the toolbar or in the menu also. So the four toolbars are available: standard, draw, format, and edit object. So you can see here one of the toolbar: reset pointer, function block, wiring, and text. So through that you can add the text. You can wire the function blocks, and this is the reset pointer. So you can see toolbar graphic function block graphic page here. This one control drawing builder, and you are selecting function block. So you have selected a PIO here. So this model name is a PIO, and this is the what actually symbol, and you can enter the tag inside this using the text in the toolbar, and click OK. So open control drawing builder to create a simple open loop. The four major icons widely used in the control drawing builder: reset pointer, function blocks, wiring, and text icons. Click on text icon, drag it on the control drawing builder, and type the required text. That's all. Means here you have to once PIO is coming here, so you just click on toolbar text, bring it here, and type it. That's all. Click on reset pointer again to come out of the text option. Step 2 is now click on the function block icon. From from the select the function block list, select the link block and select the PIO. Means I am showing this. Click on drawing pen and enter the label here. So you are here, select PIO block, this block, and click on drawing pen and enter the label here, right? And select OK. So that is what it is. The procedure is mentioned. Single click on the control drawing builder to transfer the PI block to the drawing pane. Enter the label. The label should be label entered in the IO card. Click on the reset pointer and move PI block to the required position, like this. This. So you are working here on this, and then move to this area. That's all. Select the PVI block from regulatory control. This is a creation of open loop. PVI block is the open loop. In the input indicators, click on the drawing pane and enter the tag name to the function block. Same thing. So you are in selecting function block PVI. So your PVI will be here. This. Click on drawing pane to enter the tag name here. This is the PVI block and enter the tag name, right? And say OK. Creation of open loop step 4. Click on wiring icon to select the wiring option. Select single click on the input IO connection terminal and double click on the output connection terminal to complete the wiring. So you see here, now this is your earlier input block. This is your PVI block, your open loop creation. And what you have to do, single click from the input connection here and double click at the output connection here. You automatically it comes. So select this is what toolbar. Select wiring. Wiring icon is here. You see here. This is a text icon. This is a reset, and this is a function block, right? So this is a simple open loop here. Then save the control drawing pane from the file and download the option. For creation of closed loop, PIO and PID blocks are required. Step 1, op open a new control drawing builder to create a simple loop. The four major icons which are widely used, same. reset pointer function block. Click text icon, drag it, simple closed loop, that's all, and click a reset pointer. So that is what I have shown in the open loop also. Then in the closed loop, click on the function block, from select the PIO, click OK. Like this, you can see here, uh, this is the PIO for PID. Here, click on drawing pane to enter the label. You have to enter the label tag. So this one important is here. Enter the label entered the IO card. In this case, let us consider percentage FT 900. This is analog input. Percentage FT. The percentage is there. Uh, Proprietary practices for tagging it. Hmm. Then select the PID block option. Under the regulatory control block, click OK. Single click on drawing builder to get the PID block on the drawing sheet. Right. So finally, you can see this is what you have done. Click on drawing pin, and this tag is you have entered here. And so what you have done, select the PID, this, and you have entered the tag, and then enter the tag name to the PID controller and use the another PIO for output to edit the tag. So analog input label percentage FT 900 and PID as FIC 900 and analog output as percentage FCB 900. This is a closed loop. This is input, output, and this is a PID tag. So here you will get this like this finally. Like this is what picture shows for demonstration. This is input, this is your PID, and this is output, in, out, input. So the same procedure is mentioned here. Select the wiring icon to wire the blocks. As this application built as a in a closed loop, the data of analog process input blocks will act as an input to the PID block, and output of the PID block will be input to the analog output function block. Once the wiring option is selected, single click on any one of the cross mark on the input block which acts as a source, and double click on any of the cross mark on the PID block which acts as a destination of this example. Similarly, in the text next step, select PID block as the source and analog output PIO as a destination. Single click on any of the cross mark on the PID block and double click on any one of the cross mark on the analog output PIO. The completed wiring is done as shown. Click on file download to save the application on the logic done. So this cross mark you can see, single click, double click, single click source, double click destination, like this. So this way this loop is configured. Then faceplates, you can see monitoring process where faceplates are for the PID, PIO, you can see here. Process values indicators, normal. During normal operation in auto mode, process value from field here, output of a PIO, set values are means PV, set, and output here. And same thing on bar graph, same values. This is a tag name. So this is a closed loop faceplate. So graphic window uses a graphic object to provide overall view of the plan. Graphics windows can display graphic projects, control objects, overview objects, and combination of these uh, types of the objects. Graphic objects displays the graphics. So Centum VP provides for a default graphic page, GR0001 under the Windows folder under the SIS. So you can create the graphics like this, creation of graphic view. So the libraries are available, pictures are available. You see, you just select and drag it and connect it. So GR001, this is the file, and you can take from the library various pictures like pipes, pumps, switches, tanks, walls, and so many. So you have to use that. And then once you created a graphics, you link this graphic to the required control loop. That is one of the practice is required here. So you can see area 570 is your uh, uh, this where you are linking that. So view of graphic windows, you see this way the graphics you can prepare. So that much about I have explained about Yokogawa hardware and how system is installed in the plant, what size of this plant is systems are there, and I have shown actual pictures of that, and also the software features, how control drawing builders, graphic builders used to create the graphics, used to configure the loops, open loop, close loop, PID loop. So that much was today's session. I think with this I'm finishing Yokogawa overview uh, of latest DCS. So if you have any question, otherwise, as the madam suggested, 11 o'clock we have to stop. So one more minute is there. You can ask me. Hello.
Hello, yes,
Ah,
sir.
so any question? Otherwise, we'll stop. Hello.
जाने check करा ना? Hmm?
Or you can then later on also you can ask me if because these are the sessions on virtual mode. It is difficult
Okay, okay,
to
sir.
stop me any point of view. I'm just moving forward and forward. I'm not taking pause. So if you have any question, I will definitely plan a visit, or you can mail me. I will reply it, or WhatsApp message also you can do it.
Okay, sir. No question. So thank you very much for sharing your valuable knowledge with student.
Thank you, thank you,
We will
madam.
meet
Thank
on
you.
Monday.
Okay, thank you,
Okay, sir.
thank you, madam.
करें
Thank you.
बंद देखिए.